Going to discuss about the affine map. Already we have discussed about the affine map. Here we discussed that how the affine combinations in their composition of affine map be defined. It is easily verified that the composition of two affine map is an affine map. For example, two functions f from affine space to affine space e prime and g prime e prime space to e double prime affine spaces. We have g of f of a plus v. Here a is a point, v is a fixed vector. When we apply f of a and f of v vectors, which is further apply g f of a and g vector f of v vector mappings, which show that g of f g vector of f. It is easy to show that affine map f from e to e prime is injective. Injective means 1 1. Injective means n to 1 1. Here we can easily show that the mapping from affine space to affine space e prime is 1 1. If and will have a corresponding mapping in vector space from vector space e to e prime is injective. If the corresponding mapping, for example, dear student, f from vector space e to vector space e is 1 1, then the corresponding mapping from affine space e to affine space e is 1 1 are injective. In affine map, f from affine space e to e prime is constant. F from the corresponding mapping from vector space e to e is the null constant linear map equal to 0. Here null means zero operators. For all v vector belong to E space. If E is in affine space of dimension m and a naught a1 am is in affine prime per E, then for any other affine space f and for any sequence of coordinates b0 b1 bm of m plus 1 points in f, there is a unique affine map f from e to f such that f of ai is equal to bi for I belongs 0 to m close interval. Indeed, f must be such that f of lambda naught a naught plus and so on lambda m am lambda naught b naught plus lambda m bm, where the summation of coefficient is unit is equal to 1, and this is defined a unique affine map on all of E, since a naught a1 am is an affine prime per E. Now, using affine frame, affine map can be represented in terms of matrices. We explain how an affine map f from E to E is represented with respect to a prime a naught a in E. The more general case where an affine map f from E to f is represented with respect to two affine prime a naught an in E and b naught bm in f being analogous, since f of a naught plus x is equal to f of a naught plus f vector function of x for all x belong to vector space. We have a naught f of a naught plus x, a naught f of a naught plus f of a x vector functions. Since x a naught f of a naught and a naught f of a naught plus x can be expressed as, because this relation can be expressed as x is expressed x1 a naught a1 xn a naught a1 in terms of coordinates. A naught f of a naught b1 a naught a1 bn a naught an and so on a naught f of a naught plus x y1 a naught a1 and so on yn a naught an. If a is equal to aij is the n cross n matrix of the linear map. F vector function over the basis a naught a1 a naught an, letting x y and b denote the column vector of components x1 up to xn y1 up to yn b1 to bn a naught f of a naught plus x a naught f of a naught plus f of x vectors. This system can be written in matrix form as y is equal to ax plus b. This is like a translation vector. In linear algebra, dear students, we can write this a system. We can write this. This is a 1x1. This is a 2x2. Say this is a simple b1. This is a 1 prime x1. This is a 2 prime x2. This is b2. In matrix form, we can write this a1 a2 a1 prime a2 prime this is x1 x2, and this is equal to b1 b2. Now we denote this vector by a, and this is by x, and this is equal to b. We can write this. Similarly, if here is equal to c1, here is equal to c2, then we can write this c1 c2, which we can further be write as say c vector, which is like a translations. Note that b is not equal to 0 unless f of a naught is equal to a naught. Thus f is generally not a linear transformation unless it has apex point. If his apex point, what is apex point? We say that a function f from a space x to x, when f of x is equal to x for some x, for some x belong to x, then we say that x is the fixed point of f. For example, this mapping from R to R we define as f of x is equal to f of x is equal to 1 minus x. Now here f of 1 over 2, f of 1 over 2 is equal to 1 minus 1 over 2. It means 1 over 2. It means that 1 over 2 is the fixed point of this functions. Less trivial example, consider another example for a fine map. This is x1 x2, which is map to this matrix form 1 0 0 minus 1 x1 x2 and 1 0. This is like I have written as b plus c. This map is a reflection about the x-axis. This is a reflection map followed by a translation. This is a translation. Here a translation is c and the reflection is b. B by translation along the x-axis. The affine map x1 x2 1 minus 3 under root by 4 1 over 4 x1 x2 plus 1 1. This matrix representation can be written as x1 x2, and this matrix can be further written as 2 0 0 1 over 2 1 over 2 3 under root over 2 minus 3 under root by 2 1 over 2 x1 x2, and this 1 1. And now we show that it is a composition of a rotation of angle, because 3 under root by 2, you know that this is equal to cos pi by 3, cos sin pi by 3, sin pi by 3. Now this matrix can be written as 1 over 2 is equal to cos pi by 3. So this matrix become is cos pi by 3 minus sin 3 under root pi by 3, and this is equal to sin pi by 3, and this is cos pi by 3. This is called a rotation matrix. Usually we write this is cos theta, this is minus sin theta, and this is cos sin theta, and this is cos theta. This matrix is known as a rotation matrix in 2 dimension along in polar coordinates. Here followed by a translations, it is easy to show that this affine map has a unique fixed point. The previous matrices equation has a fixed point. On other hand, the affine map x1 x2 in this matrix representation has no fixed point, even though although we can write this matrix in composition form in terms of rotation matrix as S. Here the second matrix is a rotation of angle theta, such that this is cos theta, this is minus sin this theta, this is sin theta, and this is cos theta. For sin theta is equal to 3 over 5 and cos theta is equal to 4 over 5. For more unfixed point of affine map, we can define many problems. There is a useful trick. This trick can be used for further representation. Y is equal to ax plus b into what look like a linear equation. The trick is to consider n plus 1 cross n plus 1 matrices. We add 1 is n plus 1 the component to the vector x y, and b in the form of n plus 1 cross n plus 1 matrix. This is a, and this equation can be written as a b 0 and 1, so that y is equal to x plus b is equivalent to this equation y is equal to ax plus b. We can write in matrix form as we add 1, and here we add 0 plus 1. We had this system as y1, and this is equal to a b, and this is 0 1. Now this is x and 1. We can write the system in this. This trick can be used in writing systems in equation form. Where a is a rotation, here a is a rotation, here is a is a rotation matrix. Such affine map are called rigid motions. rigid motion. Here now, students, dear student, we are going to define a ratio. This ratio formula will now be used in practical geometry. If f from E to E prime is a bijective affine map, you know that a mapping from a space to another space is bijective if f is 1 1 and on 2. Given any three collinear points, let there are three collinear points A, B, C, and E, such that A is not equal to B. These are three points. This is A, this is B, this is C. These 3 points, consider these 3 points. We say that these 3 points are collinear. Here you know that A is not equal to B and A is not equal to C. With A is not equal to B, we are say C is equal to, let this C is equal to 1 minus lambda A plus lambda B. This C is equal to 1 minus lambda A plus lambda B. Um, if this is say this is lambda, if this is lambda, this is say lambda, and this is 1 minus lambda, because if we add these two, the sum of these two is equal to 1. Now C is equal to 1 minus lambda A plus lambda B. Since f preserved by recenter, we have f of C. You know that this is a affine combination. In affine combination, the sum of the coefficient will be equal to 1. So C can be written, this C can be written in terms of linear combination of A and B points. A is 1 minus A lambda A plus lambda B. Now f of C, when we apply f of C is equal to 1 minus lambda f of A plus lambda f of B, which show that f of A, f of B, f of C are collinear in E prime. There is a converse to this property, which is simpler to state. When the ground field is k is equal to real line, the converse state that given any bijective function f from E to A prime between two real affine spaces of the same dimension in greater or equal to 2, f maps any three collinear points to collinear points. Keep in mind that if a function f from E to A prime map a collinear point to collinear points, then f is affine space. The f in B affine space. Given three collinear points A, B, C, where A is not equal to C, we have B is equal to 1 minus B. Three collinear points. Let A is not equal to C. We have B is equal to 1 minus beta A plus beta C for some unique B. Beta, and we define the ratio of the sequence ABC as. The ratio can be defined as a ratio of 3 points ABC as beta divided by 1 minus beta. AB, say this is 3 points, this is A, and this is C. Say this is C, this is B, and we define this is B and this is C. We define the B points. We define this is 1 minus beta A plus beta C. Let we denote this point B as, and here B is not equal to 1 and B is not equal to C. Keep in mind. Now the ratio of these 3 points A, B, C can be written as coefficient of C divided by coefficient of 1 minus B. This ratio can be written as. Now beta is equal to, beta can be written as in vector form. Beta can be written as from vector from A to B, because this is beta and this is 1 minus beta. This is AB in vector notation boldly, and this is BC. BC. This is a ratio formula which will be used in practice. We want our reader that rather authors define the ratio of ABC as minus ratio ABC BA BC. If we reverse, this is BA and this is BC, we can write as. Since affine may preserve by the centers, it is clear that affine may preserve the ratio of 3 points. This formula will be used later on in Siva and Thales theorem. Thank you.